In this video we're going to have a look at how vectors can be used to consider momentum and impulse problems in 2 or even 3 dimensions. It's worth noticing that the next 7 slides in the presentation actually are also part of a Unit 3 video and PowerPoint, and the only change that's been made to the slides is actually in the numbering of the examples. The end of this PowerPoint and video are the slides there are new and completely relevant to Further Maths Unit 6. The first few slides, it's a little bit ambiguous whether it's Unit 3 or Unit 6, so it's well worth being aware of the material of this video throughout. Okay, suppose we've got a particle of mass m moving under the influence of a single constant force given by the vector p. Suppose further that at t equals 0, the velocity of the particle is given by the vector u, and at time t, the velocity of the particle is given by the vector v. Then, if we use Newton's second law, we know that since there's only the one force acting, we've simply got p must equal the mass times the acceleration. And constant acceleration equations can be applied because p is constant and therefore a is constant. And if we use the constant acceleration equation, v equals u plus at, we've got the acceleration can be written as 1 over t times by v minus u. So we've now got the equation p equals m divided by t times by v minus u. In other words, we've got p times t is m times v minus m times u. M times v is the final momentum of the particle. M times u is the initial momentum of the particle. And p times t is the impulse of the force over the interval of time of length t. So, the momentum of a particle of mass m moving with velocity v is simply m times v, and the impulse acting on a body over an interval of time is equal to the change of momentum of the body. So for our first example, we have a mass of 0.8 kilograms is moving with an initial velocity 2 minus 7 meters per second when it receives an impulse of 1.6 Newton seconds. Find the velocity of the particle immediately after the impulse, and what is the change in the kinetic energy of the particle. So we know that impulse is change in momentum, so that is the final momentum minus the initial momentum. So we have 1.6 is the impulse as a vector, equals the final momentum is the mass, 0.8 times the final velocity, which is what we're trying to find, minus the initial momentum, which is 0.8 times the vector 2 minus 7. So we've got 0.8v must equal 1.6 plus 0.8 2 minus 7, which gives me 5.6 minus 4, which means that the final velocity is 7 minus 5. The initial velocity is 2 minus 7, which means that the initial speed is the square root of 2 squared plus minus 7 squared, which is the square root of 53. So the initial kinetic energy is a half times m times the initial speed squared. So that's going to be a half times by 0.8 times by 53, which is 21.2 joules. The final velocity is 7 minus 5, so the final speed is the square root of 7 squared plus minus 5 squared, which is the square root of 74. So the final kinetic energy is a half mv squared, so that's going to be a half times by 0.8 times by 74, which is 29.6 joules. So the change in kinetic energy is the final kinetic energy minus the initial kinetic energy, so that's 29.6 minus 21.2, which is 8.4 joules. In other words, the impulse has increased the kinetic energy of the particle by 8.4 joules. For our second example, we've got a ball of mass 300 grams, hits a bat at 15 meters per second and leaves the bat at a speed of 12 meters per second and at an angle of 30 degrees to the initial direction. We've got to find the impulse that the bat exerts on the ball. Well, this example certainly needs some diagrams. So let's suppose that we set up our x and y axes. So the x-axis is the same direction as the initial velocity of the ball, which means that the initial velocity of the ball can be written as a vector 15, 0. We've then got, when the ball hits the bat, an impulse j acting, and after the ball has hit the bat, it is moving at 12 meters per second at an angle of 30 degrees to its original direction, which means that we can write the final velocity as being 12 cos 30, 12 sine 30. Now to find the impulse, again, all we need to do is use the impulse equals change in momentum equation. So we've got the impulse j is the final momentum, so that's 0.3 times by the final velocity, which is 12 cos 30, 12 sine 30, minus the initial momentum, which is 0.3 times the vector 15, 0. Now if we have two particles where the only impulses acting are due to the forces of interaction between those two particles, which may be contact forces in the case of a collision between the two particles, but could equally well be gravitational forces of attraction and or magnetic electrostatic forces of attraction or repulsion. If we start off with then an initial diagram showing the masses of the particles and their initial velocities, a diagram showing the impulses acting during the period of the interaction, and then a final diagram showing the masses again and their velocities after the period of interaction, then during the time under consideration, if the left-hand particle exerts an impulse on the right-hand particle of J1, then Newton's third law states that the force, and hence the impulse, of the right-hand particle on the left-hand particle must be equal and opposite to the impulse of the left-hand particle on the right-hand particle. In other words, what we're saying is that Newton's third law tells us that the impulse J2 must be equal to minus J1. If we now apply impulse equals change in momentum to the right-hand particle, we've got J1 equals the final momentum of the right-hand particle minus the initial momentum of the right-hand particle. In other words, we've got J1 equals m2 times v2 minus m2 times u2. And applying impulse equals change in momentum to the left-hand particle, we've got J2, which is equal to minus J1, is equal to m1 times v1 minus m1 times u1. So, we've got our two equations. We've got J1 is m2 v2 minus m2 u2, and we've got minus J1 equals m1 v1 minus m1 u1. If we add those two equations, then the left-hand side is just going to become J1 plus minus J1, which is 0, equals m2 v2 minus m2 u2 plus m1 v1 minus m1 u1, which of course can be rewritten as m1 u1 plus m2 u2 equals m2 v2 plus m1 v1. In other words, we have the total initial momentum equals the total final momentum. And this, of course, is just the conservation of momentum. If a system of particles is moving in such a way that no external impulses are acting on them, then the total momentum of the system is conserved. So as our next example, we'll have an object of mass 1,000 kilograms travelling at 20 meters per second due east collides with a second object of mass 800 kilograms travelling at 40 meters per second in a northwesterly direction. Assuming that after the impact the two bodies move as a single body, calculate the initial velocity of the combined object and the kinetic energy lost in the collision. State any assumptions made in answering the question. So we'll start with a diagram. So I've got particle 1 moving at 20 meters per second due east, and we've got particle 2 moving at 40 meters per second in a northwesterly direction. After we have got the two particles combined moving with velocity v, so conservation of momentum, we've got the initial momentum of the system is 1,000 times by 20, 0, plus 800 times by minus 40 cos 45, 40 sin 45, must equal the final momentum, which is 1800 times by v. And that gives me, if we work out the left-hand side, the vector minus 2627, 22,627.4 equals 1800 times by the vector v, which means that I have the vector v is minus 1.46, 12.57. And this is the initial velocity of the combined object just after the collision. Now the initial kinetic energy is a half times 1,000 times 20 squared for object 1, plus a half times 800 times 40 squared for object 2, which gives me a total initial kinetic energy of 840,000 joules. The final speed of the two objects, in other words, the initial speed of the combined object, is the square root of minus 1.46 squared plus 12.57 squared, which is the square root of 160.14. So the final kinetic energy of the system is going to be 1/2 times 1800 times 160.14, which is 144,123 joules. So during the course of the collision, we have lost 696,000 joules to 3 significant figures. Assumptions that we've made in the course of answering this question. Well, we've certainly been treating the objects as particles, and we've certainly also assumed that nothing falls off either object in the collision. So the masses of the two objects remain the same. Moving on. A military shell moving with velocity 70I plus 15k. So the fact we've got I and k here and j later on in the question certainly means we've got a three-dimensional problem here. And this shell explodes and shatters into 3 fragments, P, Q and R, of masses 20 kilograms and 10 kilograms respectively. The initial velocities after the explosion of P and Q are 120I minus 20j plus 5k and 80I minus 30j plus 35k respectively. We've got to find the initial velocity after the explosion of R. So, since there are no external impulses acting during the explosion is purely an internal action, the conservation of momentum is applicable. So we can say that the initial momentum, which is 50 times by the vector 70, 0, 15, must be equal to the final momentum of the system, which is 20 times by 120 minus 25. That's the final momentum of P, plus the final momentum of Q, which is 20 times by 80 minus 30 minus 35. And then we've got the momentum of R just after the explosion, which is going to be 10 times by V, where V is the initial velocity after the explosion of the fragment R. So, doing some arithmetic, that now gives me the vector 3,500, 0, 750 is equal to the vector 4,000 minus 1,000 minus 600 plus 10 times V, which gives me minus 500, 1,000, 1,350 must equal 10V. In other words, V must be minus 50, 100, 135. So the initial velocity after the explosion of the fragment R is given by the vector minus 50, 100, 135, and the units are meters per second. Our final example has a particle A of mass 6 kilograms and a particle B of mass 4 kilograms, which are connected by a light inextensible string of length L meters. Initially, both particles are lying at rest on a smooth horizontal table, a distance L meters apart, with the string just slack. Particle B is given a blow of impulse 90 Newton seconds in a direction away from A at an angle alpha to the line joining the initial positions of A and B, as we can see in the diagram. Immediately after this blow, the speed of A is 5.4 meters per second. Given that the string becomes taut, prove that cos alpha must equal 3/5 and determine the velocity of B immediately after the blow. And briefly then describe what will happen if cos alpha was not equal to 3/5. Now, questions like this, we really do need a series of really good, clear diagrams. So before the impulse, we simply have A and B like that and at rest. Now the impulse diagram, well, the question's already given me part of the impulse diagram. But this impulse has got A moving. That means there must have been an impulse acting on A. This impulse acting on A must have come from the string AB. So we'll write that impulse acting on A as the impulse J. Since this is an impulse from a string, there's going to be an equal and opposite impulse acting on B from the string. So there's my impulse diagram. Now we're going to use vectors for answering this problem, so it'll be a really good idea at this stage also to mark on the axes that we're using. Now we need to start drawing the diagram showing what happens after the impulse has acted. Now first of all, we know that after the impulse, we know that A has got a speed of 5.4 meters per second. This must have been created by the impulse J, so must be in the direction of the impulse J, i.e. in the x direction, in the direction A to B. Now we don't know the velocity of B after the impulse, so all I can do at this stage is write it as an unknown vector PQ. Now, we need to give a little bit of thought to the value of P. If P is bigger than 5.4, then that means that the length of the string is going to be getting longer. The distance between A and P is increasing. If the string is inelastic, this is impossible unless the string snaps. On the other hand, if P is less than 5.4, then the distance between A and B is going to be getting smaller, so the string AB will remain slack. So for the string to be taut after the impulse, we need P to equal 5.4. Now it's important to realise that, so stop the video for a moment and try and just convince yourself of the fact that P must be 5.4. Okay then, so we've now got our diagram looking like that, and we can now start applying our impulse equals change of momentum equations. The impulse acting on A is the vector J0. The final momentum of A is 6 times the vector 5.40. The initial momentum of A is 6 times the vector 0, 0. So that tells me that J0 must equal 6 times the vector 5.40 minus 6 times the vector 0, 0, which straight away tells me that J must be 32.4 Newton seconds. Applying impulse equals change of momentum to B, well, the impulse that we've got acting on B is minus J0 plus 90 cos alpha, 90 sine alpha. And that must equal the final momentum of B minus the initial momentum of B, which is 4 times the vector PQ minus 4 times 0, 0. In other words, if we look at the x components on this equation, I've got minus 32.4 plus 90 cos alpha must equal 4 times by P, but I've already argued that P must be equal to 5.4. So that tells me that I've got 90 cos alpha must equal 54. In other words, cos alpha is 3/5 as required. looking at the y component of the impulse equals change and momentum equation for B, and remembering that if cos alpha is 3/5, then sine alpha must be 4/5, then I have got 90 sine alpha must equal 4 times q. I know that sine alpha is 4/5, so 90 sine alpha is 72 equals 4q, so q must be 18, which means that the final velocity of B is going to be equal to 5.4 in the x direction and 18 in the y direction. Now the question also asked us to briefly describe what will happen if cos alpha is not equal to 3/5. Well, we've still got the two equations that we had from impulse equals change and momentum. So equation A and equation B there. So I've still got minus 32.4 plus 90 cos alpha must equal 4p. So I've got 90 cos alpha must equal 4p plus 32.4. Now, if cos alpha is less than 3/5, then that is giving me that p must be less than 5.4, which means that the string will remain slack. On the other hand, if cos alpha is bigger than 3/5, then we've got 4p plus 32.4 must be bigger than 54, which gives me p must be bigger than 5.4, and that's only possible if the string is inelastic. That's only possible if the string snaps. So p is bigger than 5.4 with an inelastic string would tell us that the string had to snap. Okay, so that concludes our first look at vector methods for momentum and impulse. And in the next video, we'll introduce the idea of restitution to two-dimensional and three-dimensional problems.